So now we have two more circuit forms or models to add to our whole list of modeling digital circuits. And these include the reduced SOP and reduced POS forms. And again, you need to be able to go from any form I give you to any of the other forms. And you might have to go through other forms to do that. So let me give you an example here of going from a circuit diagram to reduced POS form. Okay, so let's say this is our circuit here. We're going to have two AND gates going into an OR gate. And our inputs are going to be A, C, C naught, and B naught. All right, so we want to go from circuit diagram to reduced POS. All right, the first step is, let's write the equation of the circuit as it is shown. We're getting an output F is equal to A and C, or B naught and C naught. Okay, since we want a reduced form, let's put that into our KMap. This is going to be a 3-variable KMap because we have only variables A, B, and C. And remember, we have A naught here, B naught here, and C naught here. So AC, we're going to put in the ones of the equation, is going to go here. And B naught, C naught. B naught, these two, C naught is those two. So B naught, C naught is going to go here. Okay, and then the zeros are going to go there. So if we want reduced POS, we need to circle the zeros. Oops. Nope. There we go. Circle the zeros. We can circle these two zeros and these two zeros. Great. That covers them all. So we're going to write the expression for F naught. This first one is going to be A naught C, or the second one is B C naught. We take the complement of both sides and apply De Morgan's law, and we get A or C naught ended with B naught or C. And there we have our reduced POS. Cool. So, like I said, you should be able to go from one form to another form, etc. Now, there's another thing about KMaps that I wanted to talk about, and we'll look at the textbook. This is called the Carnot maps and incompletely specified functions. So these are functions where you have inputs that you might not care about. That's what we actually call a don't care. That's the true term, don't care. And don't cares in a KMap look like dashes. And they're specified usually when you're writing it in a compact form as MD, the D for don't care. So this would tell you where to put all these dashes in your KMaps. And I'm going to go through an example here that shows you how to do groupings. Actually, I'll go ahead and just explain this example in front of us. How to do groupings with don't care. So in this example, we have a circuit which is the sum of these min terms. So the ones are entered where at the index specified here. So this is the 0, 1, this is the 7, 1, this is the 8, 1, etc. Then the don't cares are specified at these indices. So there's these dashes everywhere. Now when you do your groupings, you include don't cares as long as it helps you to make a larger grouping. So had we had zeros here instead of don't cares, these ones would have had to go in a 2-person or 2-bit group with just themselves. But now since there's don't cares, we can put them in a 4-bit group, which creates a larger reduction for us because it reduces this term to only 2 variables instead of 3 variables. Similarly here, if we didn't have this dash, this one would have to go in the grouping with this one. So again, by having this don't care, we were able to further reduce the equation. So that's how you use don't cares in the circuit. Here's another example. In this case, we're looking at the product of sums terms. Again, here, when you're using product of sums, you're going to put zeros in all these specified locations. So here is the 1, 2, and 3 zeros. And then here you can see again the don't cares are specified in these locations. So your don't cares 4 and 5 are going right here. And again, when you're doing groupings, to get the reduced POS form, you're going to be grouping the zeros. And you're making as large a group as possible, so if a don't care helps you to create a larger group, use it. So there it goes, and then these can go in a group of 4, and you get a nice reduced equation.